Hello, my name is Kevin Patton with Gallagher Fluid Seals. Today we are launching our new video webinar series for rotary sealing applications. Today's presentation will be an introduction to rotary seals. The agenda will cover rotary sealing applications, features and benefits, shaft recommendations, and housing recommendations. So, what are rotary seals? Rotary shaft seals prevent leaks by creating a seal around rotating equipment. A rotary shaft seal keeps lubricant, like oil or grease, inside the application and prevents the ingress of water and dirt. Today, there is a wide selection of designs available for use in rotary applications. They range from the traditional single and double lip elastomeric configurations to PTFE-based designs. Even more complex designs incorporate multiple lips that keep both lubricants in and contaminants out, exotic materials, and hybrid labyrinth designs. One of the most common purposes of a lip seal is to protect the bearing that is used to support a shaft in a rotating application. Retaining the bearing lubricant and keeping it clean ensures maximum bearing life and increases the overall service life of the equipment. The shaft seal often costs a fraction of the bearings in a rotating assembly. Premature bearing failure is a consistent cause for rotary equipment failure. Investing a little more money in a properly designed rotary seal, especially for challenging applications, is a wise investment. Such applications include electric motors, pumps, gearboxes, and large rolls used in steel and paper manufacturing, amongst countless others. Radial lip seals are used throughout different industries in a variety of applications under a wide range of operating conditions. These conditions can vary from high-speed shaft rotation with light oil mist to low-speed reciprocating shaft in muddy environments. Radial lip seals are found sealing lubricant oil in high-speed crankshaft applications for gasoline and diesel engines that operate from the tropics to the Arctic, in submarines, oil tankers, spacecraft, windmills, steel mills, paper mills, refineries, farm tractors, appliances, and automobiles. They can be found at anything that has a rotating shaft. So, how do rotary shaft seals work? Rotary shaft seals work by squeezing and maintaining the lubricant in a thin layer between the lip and the shaft. Sealing performance is further aided by the hydrodynamic action caused by the rotating shaft, which creates a slight pumping action. Rotary shaft seals provide protection by performing two critical functions. In most applications, the primary function of the seal is to retain the bearing or system lubricant. There are thousands of different types of lubricants available today, but in general, bearings are either oil or grease lubricated. The second function of the seal is to exclude outboard material that can contaminate the system lubricant or directly damage the bearing, causing premature failure. The type of contamination the seal will need to exclude is dependent on the application. The more common types are moisture and water, and dry materials, including dust, sand, dirt, or particulates such as those generated by manufacturing processes. The speed which the shaft rotates and the pressure on either side of the seal are two important considerations for rotary seal design. Entire categories of rotary lip seals have been engineered to seal in higher pressures and faster speeds. In general, PTFE lip seals perform better in both higher pressure and speeds, but typically cost more than elastomeric lip seals or oil seals. Pressure values above 50 psi would be considered high, and surface speeds above 2,000 feet per minute would be considered high. Next, we are going to talk about components of a rotary seal. Typical rotary shaft seal components include a rigid outer component and a flexible inner lip. See Figure 1 to 2. The seal lip can be springless or spring-loaded. Seal lips are directed at retaining the lubricant in the bearing system. Exclusionary lips face the opposite direction to exclude contaminants. Multiple lips in both directions can be designed to enhance the performance of both sealing and exclusion. The outer rigid material can range from carbon steel, aluminum, and stainless steel to a non-metallic composite as pictured here. The purpose of the outer component is to position and retain the seal in the housing. The seal's outer component must also be able to maintain a leak-free fit between the seal and the housing. The outside diameter of the seal is larger than the seal housing to create a press fit. The actual seal diameter will depend on the size and material of the seal, the size and material of the housing, and expected internal pressure and temperature. PTFE rotary seals can be designed without a metal can, and instead have a groove machined into the outer diameter of the seal. An O-ring will be inserted into this groove. Upon press fit into the bore, the O-ring will keep the seal from twisting in the housing because of the friction between the O-ring and the bore. At a certain rotational speed, this friction will be overcome, requiring a more robust press-fit design. The contact lip is designed to run on a thin film of oil. Without the oil film, the seal lip will run directly on the rotating shaft and generate excessive friction, and if the lip is made of an elastomer, could fail within hours. The lubricant selected needs to remain viable over the expected service life. If the underlip temperature exceeds the lubricant rating, carbonization of the oil will occur. Abrasive carbonized oil particles will build up at the seal lip and accelerate lip and shaft wear. As the oil film becomes less than optimal, the lip friction increases, as does lip wear. When selecting a lubricant, keep the following in mind. The temperature limits of the lubricant should match the underlip operating temperature of the seal. The base oil and additives should be compatible with the lip material. The oil level should provide adequate lubrication and cooling at the seal lip. PTFE rotary lip seals do not require a lubricant because of the unique properties of PTFE. Over time, amounts of the PTFE material from the lip will wear on the shaft, forming a layer of PTFE which enhances the sealing performance of the seal. Very challenging applications will engineer this dynamic into the design of the seal, requiring a certain amount of, quote, break-in after seal installation before the system will perform optimally. A proper shaft finish provides small pockets to hold the needed oil film between the lip and the shaft, preventing direct contact that would otherwise cause friction and wear as the shaft rotates. The shaft surface must also be smooth enough to avoid peaks that are large enough to break through the lubrication film. The optimal surface for elastomeric shaft seals is a plunge ground finish of 8 to 17 micro-inch RA with a lead angle below 0.05 degrees. Recent studies show that the RA measurement alone is insufficient to quantify a proper surface. For more information on shaft finishes and design, please view the GFS series on dynamic sealing and hardware. Typical radial shaft seals are pressed into the bore to assure proper OD sealing and seal retention in the housing. The most used materials for seal housings are steel and cast iron. Care should be taken when softer materials, such as aluminum, bronze, or plastics, are used for the housing material. Aluminum has a thermal expansion rate almost double that of steel. Steel case designs can lose their required press fit in an aluminum housing when they go through thermal cycles. A seal with an aluminum, composite, or rubber-covered OD should be used for aluminum housings. These materials help maintain the press fit in the housing during thermal cycles and reduce the possibility of galvanic corrosion. Plastic housings can also expand at a rate that can create problems if a metal OD seal is used. A good rule of thumb is to use the same material for the seal case as the rotary hardware. This ensures equal levels of thermal impact on both seal and housing. Here are some other rotary seal shaft considerations: shaft tolerances, underlip operating temperature, seal torque, internal pressure, shaft speed, shaft to bore misalignment, and shaft runout. All of these, if improperly considered, can cause premature failure of the seal and thus premature failure of the entire rotary assembly. Chapter 4 of this series focuses on rotary seal failure modes in greater detail. Thanks for watching the introduction to rotary seals from Gallagher Fluid Seals. To purchase many rotary seal profiles, head over to our website at www.gallagherseals.com. Tune in for our next video where we will discuss bonded oil seals, clipper oil seals, and closure oil seals.